Okay, this problem reads, suppose you have a 120 kilogram wooden crate resting on a wooden floor. What is the maximum force you can exert horizontally on the crate without moving it? And part B says, if you continue to exert this force once the crate starts moving, so we break that static friction and we exert that same force, what would be the acceleration of the crate? Okay. So this is a question looking at using friction as part of our force analysis. And so with a force analysis, remember the first thing we're going to identify is what is our object of interest? Well, our object is that wooden crate. So we'll draw a picture. Here's the crate. It's on a wooden floor. We're told that the mass of the crate is 120 kilograms. And it's wood on wood. And so what we need to do is look up what the coefficient of friction is for wood on wood. And we find, if we look that up, that the static coefficient of friction for wood on wood is equal to 0.5. And the kinetic coefficient of friction for wood on wood is 0.3. So you have to look those two values up. All right. We have our object of interest. Let's identify the forces that are interacting with this object because we're asked what maximum force can we exert so that the crate just prevents itself from moving. So what are some of the forces? Well, we know that the crate is interacting with the earth. So we have the crate interacting with the earth. All right. What other force do we have? Well, we have the crate interacting with the floor. That's that normal force. So we have the crate and the floor. Other forces, we're going to be pushing that force. So we have the force of the push. That's between the crate and the pusher. So you in this example. And then we have the force of friction. We said that friction is present. And for part A, what type of friction is it? So that's between the crate and the floor, and we're the maximum force before it starts to move. That means it's not moving. This is static friction. All right, so what's our next step? We're going to draw a free body diagram on that crate. Here of the crate. There's my crate. All right, we have the force of gravity that acts in the downward direction. Remember, that's equal to mg. That's the crate's weight. We have the normal force. It's resting on that horizontal surface. So that's going to be in the upward direction. We're pushing the crate. I'm going to say we're pushing it to the right. So we have the force of the push. And then we have that frictional force acting in the opposite direction. And we know that is our static frictional force. Perfect. So we're going to do our force analysis. We have 1, 2, 3, 4 forces we have to deal with. We're going to look at our horizontal and vertical components to those 4 forces. All right, force number 1, nothing's happening horizontally. It is pointing in the negative direction downward. And so we're going to put negative in or be explicit in our direction of the force. Force number 2, positive force of the push, and nothing is happening vertically. Force number 3 is purely vertical, upwards, that positive direction. And force number 4 is to the left, and nothing vertically. So now that I've separated into their 2 components, the sum of the forces horizontally is the mass times the horizontal acceleration. The sum of the forces vertically is the mass times the vertical acceleration. Now, this is the part A is the crate isn't moving. What maximum force can we exert for it to not move? And so the acceleration horizontally is 0 and that acceleration vertically is 0. I'm going to bring that down. We have the force of the push minus the static frictional force. And if we're at a maximum force, that's going to be our maximum friction, is equal to 0. So we know that the force of that push is going to equal the static friction force. Well, friction is fun. Remember, friction is mu times n, fun. And if we're dealing with maximum static friction, it's equal to mu times n. It can be less than or equal to the maximum. So this is at the maximum situation, which we are in if we're just preventing motion. So that means the force of the push, what we're interested in, is equal to mu times that normal force. So we need the normal force. Well, that's in our vertical dimension. We have the normal force minus mg is equal to 0. So our normal force is equal to our mass times our gravity. Now we're given a mass of 120 kilograms. So mg is equal to, I don't have that in my notes. I'm just going to move it here because my answer key and I don't have a calculator. We're going to pop that into that equation. We have the force of the push is equal to mu of sub s times m times g, which gives us a total of 588 newtons. So mu times mg is 588. Remember that mu was our 0.5. So this is a static frictional force times 120 times our 9.8. All right, so recognizing we're in the case of static friction, maximum static friction because we're just preventing that motion. What maximum force can we exert before that box starts to slide? Okay, so part B, that was part A. Part B says, well, if I keep applying this force, what will the acceleration of the object be? So we've just broken static friction. And what do we want to keep in mind about static friction as compared to kinetic friction? We know that our coefficient of static friction is greater than our coefficient of kinetic friction, and we see that in our values that we looked up for wood on wood. But we know that because in our experience, we know that it's easier to keep something moving, sliding our furniture across our bedroom, than it is to get it to move. That kind of, I gotta get it to move situation. So I'm just gonna get part A out of here. All right. So what about this problem really changes? And we can start this whole problem over, but in the interest of our time, what about the problem really changes? Well, in this case, we're still applying a force, so we still have the force between the crate and the pusher. There's still a force between the crate and earth and still a force between the crate and the floor. And we still have friction present. But instead of this being static friction, the crate is now sliding along the floor. We're in a case of kinetic friction. And for kinetic friction, the coefficient times the normal force is equal to the kinetic friction. So we're just going to adjust, and I would encourage you to restart the problem so that you get good practice. But everything about the problem actually is the same, except now we're dealing with kinetic friction instead of static friction. So if we do our list, we still have the force of gravity, which is in the vertical direction, downward. We still have the force of the push, and now we're going to use that value. This was 588 newtons. We said, what will be the acceleration if I break static friction, but I maintain my force of 588 newtons? So we had to go a little bit further to break that static friction, but then we went to that 588 newtons to maintain the motion of the box once I got it moving. The normal force, of course, is in the vertical direction, and then we have the kinetic frictional force times in the horizontal direction, not the vertical direction. All right, so again, the sum of the forces horizontal is the mass times the horizontal acceleration, And the sum of the forces vertical is the mass times the vertical acceleration. Now we're still not changing our motion up and down, so this is indeed 0. So our normal force minus mg is equal to 0. So the normal force is still equal to mg for our example. Horizontally, however, we have the force of the push minus the kinetic frictional force is going to equal the mass times the horizontal acceleration. So we want to determine what is that horizontal acceleration. We know the force of the push is equal to 588 minus the kinetic frictional force is going to equal 120 times that horizontal acceleration. Well, our kinetic frictional force is equal to mu sub k times n or mg. And so when we determine that, our kinetic frictional force using our coefficient of kinetic friction is 352.8 newtons. So I can plug that in here. We have 588 minus 352.8 is equal to 120 times that horizontal acceleration. And when I solve for the horizontal acceleration, I get 1.96 meters per second squared. So recognizing that the free body diagram looks very similar, but now we're dealing with a case where we're moving or sliding that object. And so we're going to use our kinetic friction. Our kinetic friction uses our kinetic coefficient, which conceptually in a previous video or in the mini lecture on friction, we talk about why the coefficient of static friction and the coefficient of kinetic friction are different. So I encourage you to check that video out and then utilize that relationship to solve for the acceleration in the horizontal direction. All right, good job.